In this section, we're going to look at another conic section called an ellipse. And an ellipse is a oblong kind of circle, and it's uneven in its two dimensions. It doesn't have a constant radius like a circle does. What it has is this distance here across, and then it has a different distance going the other direction. And so it doesn't have a constant radius. What it does have is a constant value is if you take these two points called the foci or foci, and that's the plural of focus. The focus is similar to the focus in a parabola in that it's inside the curve, and it always occurs on the longer axis. So if this right here is called the major axis, the longer one, and then the shorter one is called the minor axis. And the ellipse can also go this direction, which is called a vertical ellipse as opposed to a horizontal ellipse. And this one, it has a vertical major axis and a horizontal minor axis. So the longer one is always called the major axis, the shorter one is always called the minor axis. The foci will always be on the major axis. And some other names are on the ends of the major axis, you have the vertices. So there's two vertex points. Then you have the other ends of the minor axis are called the co-vertices. And so the co-vertices would be here, and the vertices would be here, and the foci are inside the curve near the vertices. Back to the constant distance I was talking about. What stays constant is if you take any point on the ellipse and measure its distance to the focus and then its distance to the other focus. Let's call this distance m and this distance n, that little line segment. If you take m plus n, that will remain constant throughout the entire ellipse. So that is your constant value instead of a radius like on a circle. The thing that will stay constant is the m plus n. So if I took another point, let's say over here on the ellipse, if you measured this distance and you measured this distance and added them together, this would be like your m and your n, then that would be the same amount as the other m plus n. So that is the thing that stays constant. Therefore, the way an ellipse is defined is an ellipse is the set of all points in a plane such that the sum of the distances to the two fixed points, which are the foci, is constant. So that sum of the two distances from any point on a plane to two fixed points creates the ellipse. Now we're going to relate the figure to an equation. And in our equations, on all conic sections, we're going to have the center of your figure is going to be HK. And on a parabola that we've done previously, a parabola, the center was the vertex, and so we called the vertex HK, but it is truly the center of the parabola. The center and the vertex are the same point. However, in an ellipse and a hyperbola that we're going to do next, HK is called the center, where the vertex is in a different location, like we talked about on the previous page. So the center in a ellipse that is centered at the origin, the center is the origin, 0, 0, and that is your HK. But we're going to, as every figure, we're going to end up transforming these and moving them away from the center at the origin, and the center may be some other point, HK. But just remember the center goes with the HK. The vertex, however, is over here, and we've got two of them. And this distance between the center and the vertex is considered our A value. So remember that between the center and the vertex is our A value. Then we have our co-vertices, remember, on the short axis, the minor axis, and the distance between the center and the co-vertex is considered to be B. So even when the the ellipse is going in a vertical direction, you call the distance between the center and the vertex, this distance would be A, and between the center and the co-vertex, this distance would be B. So on ellipses, A is always going to be bigger than B because A will always be on the major axis between the center and the vertex. If you watched the video about parabolas in the conic section chapter, what we called little c had to do with the focus. And I talked about the letter C being in the word focus, and so remember that focus always has to do with the letter C. The same applies here in that C has to do with the focus. And so what's going to happen is the distance from the center out to the focus, which is here, will always be the distance little c. So I say little c as opposed to big C, which is the center point. Little c is just an amount, and it's the distance between the focus to the center. So we have an A, a B, and a C. And what's interesting is if you need to find where C is or what that amount is, you're going to use A and B, which are always obvious from the equation of an ellipse. You're going to use the A and the B to help you find the C. Just like in a parabola, we used A. We didn't have a B, but we used A to help us to find C. And we're going to do a similar thing with A and B to help us to find C. And the funny thing is, it's very similar to the formula that is the Pythagorean theorem, but it's a little bit different in that you have c squared will equal, instead of a squared plus b squared, it'll be a squared minus b squared. So very similar to the Pythagorean theorem, a squared plus b squared equals c squared, except you do a squared minus b squared. So I just wanted to point that out, that it's similar to something you already know, but it has a minus sign instead. Some other important features of the ellipse is that if you think about it, if this distance is A from the center to the vertex, well then the length of the major axis, if they ask for the length of the major axis, which they sometimes do, it would be A plus A, which would be 2A. So the length of the major axis equals 2A, because it's double the A, which is the distance from the center to the vertex. And the length of the minor axis then would be B plus B, and so you'd have 2B. And the interesting is that constant value we talked about on the previous page, that m plus n, happens to equal the 2a. So if you ever needed to know what that constant value is that remains the same throughout this particular ellipse, it would be the value 2a. And let me just show you why real quick. Let's say the point that we chose on our ellipse was the vertex instead of some random point on the ellipse. Let's choose the vertex as our point that's on the ellipse. Well, its distance to the first focus is this little amount right here, and its distance to the second focus is this amount right here. And if you add those two pieces together, you really get the same as the length of the major axis, because if you took this little piece and added it over here, you would get the whole major axis. And so it is the same length as the major axis, the m plus n. So if I could figure out what this value was plus this value, that would also be whatever 2a is. So that's just an extra piece. You won't be asked that very often, but if you ever wanted to know what that constant value is that remains the same throughout the ellipse, it's the 2a. So now let's look at how all these A, B's, and C's kind of work into a formula for the equation of an ellipse. So all the conic sections will have this piece here that's x minus h and y minus k. If, like in the picture, the center is at the origin, then the h and k will just be 0, 0, and you'll just have x squared and y squared with no h and k involved. And so that'll be the most simplified version before we move the ellipse off of the origin. But this is the general formula for any ellipse, whether it's moved off the origin or not. And it's x minus h squared and y minus k squared, which is similar to the pieces that you'll see in other conic sections. And the difference is you'll have this fraction, and on the bottom of the fraction you'll have an a squared and a b squared. And sometimes they'll switch, and the b squared will be here and the a squared will be here. And then you'll always have an equals 1 out to the side. And if it's not in this form, you can rearrange it into this form by dividing by whatever you need to get a 1 on that side. But this is a formula in the equation of a ellipse. Now, the way you know which direction the ellipse is going, which is the important first thing to notice, is which direction is it going. Is it a horizontal ellipse or a vertical ellipse? The way you can tell is where the A is, because A is always going to be bigger than B, because the way we define A in an ellipse is that it's the distance between the center and the vertex, which is always on the major axis, so A always has to be bigger than B. So you look for, because they're not labeled A and B, you look for the bigger number that's underneath the different fractions. And when you find the bigger number, you know that one is going to be the a squared. And then you find the smaller number, and you know that one's going to be the b squared. Then you can square root it to find out what the actual a is and the actual b is. So on the first example that I have here, this one has the bigger number under it. And because the bigger number is under the x, then the major axis is going to be in the x-axis direction, which is horizontal. It's sideways. Now, on the other one, the bigger number is going to be under the y, which tells you that the major axis is going to be in the direction of the y-axis, so it's going to be vertical. So this one is a horizontal ellipse, and this one is a vertical ellipse. It all depends where the bigger number is, which is called our a. So that's the foundation that you need to understand ellipses, and we're going to do some examples in the ellipses part 2, where we do different examples and see how all this plays out.